Down and chat with one of the members of the Department of Meteorology here at Penn State. And we're fortunate this evening to be joined by one of the newest members of the faculty, Dr. Chris Forrest, who came to Penn State in the fall from MIT. Welcome to Weather World, Chris.
Thank you very much.
Good to have you.
Be here.
Now, your official title is kind of interesting, Associate Professor of Climate Dynamics. Exactly what does putting the dynamics on the end there meant to imply?
Well, I thought about this a lot when I first started to, put together my statement about what I wanted to do when I came here. And I knew that the work that I do the most is actually dealing with the climate system. And I know that the climate system isn't a static thing. And so instead, people have a lot of trouble trying to remember whether it's climate science or climatology or the Earth system or things like this. And I think my main interests happen to be in how the climate system changes with time, and specifically what happens in the future or in the past, and so over the past 100 years, the next 100 years, and those sorts of issues.
Okay.
So dynamics kind of captures that ability to say that it's not a static environment.
Right.
We're not talking about just the last 30 years and what the averages are. We're actually looking at how it's going to be changing with time and how the different systems interact with one another.
And you mentioned prediction. You know, when the topic of predicting climate change comes up, people look at me and they say, you guys can't even forecast the weather 3 days in the future. Why are you even thinking about decades in the future? What's the best way to kind of get people to think about that?
What I try to do, I always get puzzled by it myself. So what I try and do is say, well, they're really two different questions. Forecasting the weather is actually forecasting the state of tomorrow's precipitation, rain, weather, wind, and so on. Predicting the climate is much more about how the system is in balance, whether or not the total incoming sunlight is balanced by the outgoing long-wave radiation on the Earth. And so we're really much more interested in that long-term prediction of how the system is in balance and how it's going to be changing with time. And as opposed to, and the models that we're developing actually have a different set of criteria for how that's going to work.
Okay. What I find interesting about your work is you're taking sort of a probabilistic approach to modeling climate change, kind of acknowledging the uncertainties.
That's right. And
then trying to quantify them. What are the various sources of uncertainty in climate change modeling?
Well, there are two issues. One is that you have the climate system is being forced by changes in greenhouse gases or changes in local land use or changes in aerosol over time. And so you have to talk about the uncertainty and the forcings as one part of the problem. And then there's the response to those forcings, which is what we do as scientists to try and understand how the system is going to behave as these forcings are changing with time.
And how do you try to quantify, put a number on those uncertainties? Because that seems very challenging.
That's the toughest part, and those are the research questions that we really have to dive into. And the best way to do that is to try and do what we call hindcasts, or predictions of what's happened over the last 100 years. And by doing so, we have the variability of the weather, we have the variability of the climate, we have which has to be considered into quantifying the uncertainty, as we call it. So we get into a lot of the statistical problems associated with that, of comparing the climate hindcasts with the record of observed changes since during the last century.
Okay.
And it's very similar to the weather problem of producing a skill score. You're trying to decide what fraction of the time are you going to be producing a simulation that's appropriate for that's matching the observed record, and how much of the time are you going to be producing a simulation which has nothing to do with what we observed in either the surface temperature or the oceans or other parts of the climate system as well.
Well, what about the uncertainty from the spatial perspective? Another question I get a lot is, well, what can you folks tell me with some degree of certainty about what climate change might bring? And then they mention their specific county in Pennsylvania. Absolutely. Or their specific region. I mean, what about that kind of uncertainty?
So there's spatial, what we call that is the homogeneity problem, or the heterogeneity problem. And it's clear from the work that I've done is that we really want to be looking at things on the largest scales. We want to look at the global problem, and we want to be looking at sort of average temperatures or average precipitation across the hemisphere, as opposed to actually trying to look down at the small regional scales. But the skill of the models is getting much better. The quality of the models are now able to produce what we would call the weather forecasts from maybe 20, 30 years ago are sort of the spatial scales which are being resolved in the climate models now. And so we're actually able to look at the temperatures on maybe not the county scale, but we're certainly looking at the size of New England.
The regional scale.
Maybe it's tough to even get down to the size of Pennsylvania, but the regional scales, you sort of divide the United States up into, say, 6 major regions, and those six regions we're able to actually predict what's happened over the past 100 years with pretty good accuracy. Okay. And I think as the research evolves, as the data comes in from satellites, from the observational networks, we're actually going to start seeing much more ability, much more skill at those smaller scales.
Okay. Dr. Chris Forrest, thanks for
you.
stopping by Weather World.
Thank you very much.
Welcome to Penn State.
Thank you very much.
We'll be back in a moment with a recap of the short-range forecast.